Hello! Today we're going to dive into ionic compounds. So last time we saw that atoms can lose or gain or share electrons in order to achieve an octet of electrons in their highest energy level. So we saw that there are some predictable charges. So for instance, everything in group 1 can lose one electron to become like a noble gas and have an octet of electrons. And we also saw that nonmetals can gain electrons in order to become like a noble gas. So now we're going to see that metals and nonmetals can actually form what's called an ionic bond. Ions with positive charges are attracted to ions with negative charges. And this is kind of similar to our previous discussions of protons and electrons. We know that protons and electrons are attracted to each other because of their opposite charges. And this is the same for ions. So if you have an atom with a positive charge, that's going to be attracted to an ion with a negative charge. Now, one thing that I didn't put on here is ions with positive charges are called cations, and ions with negative charges are called anions. So one cute way to remember this is cations are positively charged. Maybe I'll draw a little nose there for the cat. Okay, so the attractive force between the positive and negative ions is what holds them together, and that force between them is called an ionic bond. So ionic bonds form between simple ions when a representative metal loses valence electrons, and then a nonmetal is going to gain those electrons. All right, so for instance, down below we have what's called sodium chloride, or table salt. So this is what you put on your food if you salt your food. And sodium, we saw last time, has 1 valence electron, and chlorine has 7 valence electrons. So sodium wants to lose its outer valence electron in order to become like a noble gas, and chlorine, we saw, wants to gain 1 electron so that it has 8 electrons like a noble gas. So what can happen is sodium can give its electron to chlorine, and you can see that with this arrow here. And eventually, we're going to form a positively charged sodium ion and a negatively charged chlorine ion. All right, now once the two form a compound, then their charges will cancel out, and the overall compound will have a charge of 0. So typically, ionic compounds do have a charge of 0, or another way of saying that is an ionic compound is neutral. So we always want the positive charges to match the number of negative charges. Okay, so let's look a little bit more closely at sodium chloride. So if we want to make sodium chloride, we would start with pure sodium and chlorine gas. And we saw previously that chlorine gas has sort of a yellow-green color to it. And chlorine gets its name from the word chloros, which in Greek means yellow-green. So if we mix these two together, this is actually a very exothermic reaction, which means it gives off a lot of heat. So you can kind of see that over here. And I think I showed you an example of this reaction on that Theodore Gray app as well. So it's pretty explosive. Now, once we combine these two together, we get our sodium chloride compound. And you'll notice that these little gray atoms are sodium ions, and then the green spheres or atoms are chlorine ions. And so they're alternating and kind of surrounding each other to form what's called a crystal lattice. So the stable form of an ionic compound is actually not a molecule, but a crystal in which many ions of opposite charge occupy what are called lattice sites. And this forms a rigid three-dimensional arrangement called a crystal lattice. So even though we write sodium chloride as NaCl, so this is its chemical formula, we don't actually have individual sodium chloride molecules. We actually have this really large crystal lattice with alternating ions. So again, you can see each sodium ion is surrounded by chloride ions, and each of the chloride ions are surrounded by sodium ions. However, they exist in a 1-to-1 ratio, which is why we write it as sodium chloride, or NaCl. So sodium chloride and other ionic compounds that only contain two types of elements or ions are called binary ionic compounds. So again, when ionic compounds are formed by the reaction of only two types of elements, this is called a binary ionic compound. So down below we have a couple of examples of binary ionic compounds. So both of these contain copper and oxygen. So you'll notice on the left there's actually two copper ions and one oxygen ion. And on the right there's only one copper ion and one oxygen ion. And this can create a huge difference in the type of, or the properties of the compound. So on the left, if we have two coppers bound to one oxygen, we get a greenish compound. And on the right, if we only have one copper bound to oxygen, then we get a blue compound. And what we're going to talk about in a bit is the fact that, or actually in the next lecture, is the fact that some transition metals can have more than one charge. But for now, just keep in mind that there are different types of binary ionic compounds, even if you have the same two elements. All right, so let's talk more about balancing charges in ionic compounds. So what if we were creating a compound between sodium and sulfur? We already saw that sodium is a group 1A metal, and it loses one valence electron to form the sodium ion, which is Na+. So sulfur, you might remember, if we draw the Lewis symbol, sulfur is in group 6A, so it has 6 valence electrons. And it needs 2 more electrons in order to have an octet. So we'll draw those 2 other electrons in blue. Now when it gains those 2 electrons, we've changed the ratio of protons and electrons. So now we have a 2 minus charge because we have 2 extra electrons there. Now, if we want to create a compound between sodium and this sulfur ion, we need to make sure we have the same number of positive and negative charges. So in order to balance the charges, we have a 2 minus charge. So that must mean we need 2 positive charges so that everything adds up to 0. So what that tells us is we are going to have, one sulfur ion and 2 sodium ions. And the resulting formula will be Na2S. And down below we can see a picture of the formation of this ionic compound. So again, sodium loses 1 valence electron, and it gives it to sulfur in this case. But sulfur needs 2 extra electrons, so it's going to take the other electron from a different sodium atom. And remember, sodium can only lose 1 electron because once it loses that 1 electron, it becomes stable like a noble gas. So it's not going to lose any more electrons. So then sulfur has to go to a different sodium atom in order to gain another electron. And again, we end up with 2 positively charged sodium ions and 1 negatively charged sulfur ion. And their charges all balance. And then we would call this compound sodium sulfide, and we'll get into naming later on as well. So let's do an example problem. We're going to write the formulas for the following pairs of ions. So potassium and fluorine, calcium and oxygen, calcium and fluorine, and potassium and oxygen. If you want to try this on your own first, you can pause the video and then you can see if you got the right answers. Okay, so you might recall that potassium is in group 1A and fluorine is in group 7A. So that means that potassium has 1 valence electron and fluorine has 7 valence electrons, and I'm just drawing those Lewis symbols here. So potassium is a metal, which means it wants to lose electrons. And fluorine is a nonmetal, which means it wants to gain electrons. And if you're not sure how I determined whether these were metals or nonmetals, you might want to go back to chapter 2 or, chapter 3 and kind of look over some of the information there. Okay, so remember that everything wants to be like a noble gas and have 8 valence electrons, except for hydrogen, which only wants 2. But in general, everything wants 8 electrons. Now, if potassium loses 1 electron, its valence electron, it becomes a positively charged ion because it has 1 less electron, so that means in that case we have an extra little proton hanging out with a positive charge. And then fluorine, when it gains an electron to have 8 total valence electrons, it will have a negative charge. So in order for these 2 ions to balance each other out, we just need 1 of each. So we would have Kf as our chemical or compound formula. Now, what about calcium and oxygen? Oh, let me change my marker color here. So calcium is in group 2A, and oxygen is in group 6A. So calcium has 2 valence electrons, and oxygen has 6. 1, 2, 3, 4, 5, and 6. So again, calcium is a metal, so it's going to lose electrons. And oxygen is a nonmetal, so it's going to gain electrons. And I'm actually going to make some room up above here. I kind of didn't give myself enough. Let me rewrite Kf. So if calcium can lose 2 electrons and oxygen wants to gain 2 electrons, we're going to end up with a calcium 2+ ion and then an oxygen 2- ion. And what's great is those 2 charges balance each other out. We have 2 positives and 2 negatives. So our overall formula will be CaO. And you might remember this from a previous homework assignment too. All right, so now for calcium and fluorine. So we already said that calcium has 2 valence electrons and wants to lose those electrons. And we already said that fluorine has 7 valence electrons and it wants to gain 1. So the resulting ions would be Ca2+ and F-. So how many calciums do we need and how many fluorines do we need in order to balance the charges? So we need 2 negative charges to balance those 2 positive charges. So we're going to write CaF and then put a little subscript 2 next to fluorine to show that we have 2 fluorines. Okay, and then in the last problem, we already said that potassium wants to lose 1 electron and oxygen wants to gain 2 electrons. And so that will form a potassium ion and then an oxygen ion with a 2- charge. So how many potassiums do we need and how many oxygens do we need to balance the charges? So we need 2 potassium ions to balance the 2- charge on oxygen. So we're going to write this as K subscript 2 O. Okay, so hopefully that helps a little bit with seeing how we determine these different formulas. And again, it really is just all about knowing the different charges that each atom would have as an ion. And then, and you can determine that by the group numbers. And then you need to make sure that the charges balance each other because ionic compounds are going to typically be neutral. And here is the solution slide if you need that later on. Now, there is one more thing I wanted to cover, and those are polyatomic ions. So polyatomic ions are interesting because we have a group of atoms bonded together with an overall charge. So for instance, this down here is the hydroxide ion. So we have 2 elements bonded together with an overall negative charge. So instead of just one element with a charge, we have two. And you'll also notice, for instance, this one over here, H2PO4 minus, this one has, let's see, 2, 3, 7 atoms bonded together with an overall negative charge. Now, the type of bond that's occurring between those elements, those are covalent bonds. So all of those atoms are sharing electrons. And we'll talk more about covalent bonds in a future lecture. But the main idea here is that a group of elements can have an overall charge. Now, polyatomic ions are pretty common in chemistry, so I would like you to know the different names for these polyatomic ions. Now, obviously, because we're online, I can't control whether you have a table of polyatomic ion names in front of you, but I will post some flashcards on Canvas so that you can practice learning the different polyatomic ion names, because it is really important to know them in chemistry. All right, so a few of the polyatomic ions that come up quite a bit are, for instance, ammonium, acetate, carbonate, let's see, bicarbonate is a really important polyatomic ion. That's what helps regulate how acidic or basic our blood is, and we'll talk about acids and bases later on. Hydroxide is important, nitrate, phosphate, and sulfate. So those are a few of the more common polyatomic ions that we'll see. All of these are common, but those few that I underlined come up quite a bit. Okay, so if we have a polyatomic ion, so a group of elements with an overall charge, we often see compounds that are neutral that contain a polyatomic ion. So the rules for writing formulas for ionic compounds containing polyatomic ions are essentially the same as those used for writing formulas for binary ionic compounds. So the symbol for the metal is written first, followed by the formula for the negative polyatomic ion, and then equal numbers of positive and negative charges must be represented by the formula. So very similar to what we were doing before. Now, when more than one polyatomic ion is required in the formula, parentheses are placed around the polyatomic ion before the subscript is inserted. But you only need parentheses if you have more than one of the polyatomic ion. If you only have one polyatomic ion, you don't need the parentheses. Now, remember, we do have one positively charged polyatomic ion, so let's go back. So in this table, you'll notice that all of the polyatomic ions have negative charges except for ammonium. It has a positive charge. And so ammonium can actually take the place of a metal ion because it has a positive charge, and metals are usually positively charged. All right, so when you are memorizing the names of these polyatomic ions, you also want to memorize these formulas and their charges, because knowing those charges will help later on when you're determining a formula. Okay, so let's look at these examples down below. So in each of these compounds, we have PO4. This is the phosphate ion, and it has a 3 minus charge. So in this first compound here, we have 3 sodium ions and 1 phosphate ion. Oh, my pen is not working. There we go. So you'll notice that those 3 positive sodium ions balance the 3 minus charge on phosphate. In the second compound, we have 3 magnesium ions. And remember, magnesium is in group 2A, and it has a 2+ charge in its ionic form. Now, the reason that we need 3 of those magnesium ions, we have 2 phosphate ions, each with a 3 minus charge. So we need to balance this overall 6 minus charge with a 6+ charge overall from those 3 magnesium ions. And then in the last compound, we have 1 phosphate ion, which is PO4 3-, and ammonium, remember, just has a positive 1 charge, so we need 3 of those to balance the charge on phosphate. So this gives us an overall +3 charge. You'll also notice that when we have multiple phosphate ions in the second compound, we had to put parentheses around phosphate and a subscript 2 next to it. Now, the reason that we do that is, let's say we just wrote PO4 2. It looks like we have 42 oxygens bonded to that phosphorus atom, and that doesn't quite make sense, right? So we want to make sure that we're separating phosphate from the subscript. Now, if we just have 1 phosphate, like in the first compound here, we don't need parentheses because we're not trying to separate phosphate from a subscript. And then in the last compound, we had multiple ammonium ions, so NH4. So we also needed parentheses to separate it from the subscript. Otherwise, it would look like NH4 3, and it would look like we have 43 hydrogens bonded to nitrogen. So we want to make sure we put parentheses around the polyatomic ion. Okay. So let's do an example problem where we try to balance the charges between a metal ion and a polyatomic ion, and then we're going to write the formula. So if we have, in our first example, potassium with a positive 1 charge, and let's look up the name of ClO3. So let's go back to this chart. Okay, so ClO3 is right here, and this is called chlorate. Okay, so let's see what our formula would be here. How many potassiums do we need, and how many chlorates do we need to balance the charges? Right, we just need 1 potassium and 1 chlorate. So the chemical formula, or the compound formula, is KClO3. Now, what if we have a calcium 2+ ion and a chlorate ion? How many calciums do we need, and how many chlorates do we need to balance the charges? We need 1 calcium and 2 chlorates. Now remember, if we write ClO3 2, that looks like we have 32 oxygens. So we're going to put parentheses around ClO3. separate it from its subscript. Okay, now in the last problem, this is a bit of a challenge problem. We have a calcium 2+ ion and then a phosphate ion, which has a 3- charge. How many calcium ions do we need and how many phosphate ions do we need to balance the charge? Right, okay, so if you're a little confused on this one trick I have is take the superscript charge and turn it into a subscript. So, for instance, if we have a calcium 2+ charge and then a phosphate 3- charge, we have too many negative charges there, so we need to add another set of positive charges. But now we have an overall 4+ charge from our calcium ions and only a 3- charge from phosphate. So we need some more negative charges to balance the positive charges. But now we have too many negative charges. We have 6- overall and only 4+ overall. So we're going to add another calcium. And now we have an overall 6+ charge from those calcium ions and an overall 6- charge. So we should have Ca3 parentheses PO4 2. So you'll notice we're kind of trying to find a common factor here between the ions. And so this is one way to do it where you just flip the superscripts into subscripts, or you can draw a picture like I did on the right, whichever way works for you for figuring out how to balance those charges. Okay, so these are the answers if you need them later. And I think we're going to stop there today. Next time, we'll talk about ionic compound formulas and how to determine the mass or weight of an ionic compound. So I will see you in the next video.